When dealing with 230 volts motors connected to a 208 volt supply, several potential solutions exist. Firstly, consider using a step-up transformer. Installing a step-up transformer converts the 208 volt supply to the required 230 volts. This approach necessitates the incorporation of additional electrical components and wiring to accommodate the transformer. Secondly, evaluate the option of installing a voltage compensator. Connecting a voltage compensator to the motor terminals boosts the voltage to the desired 230 volts. However, it's important to recognize that this method may lead to a reduction in the motor's overall efficiency and potentially shorten its operational lifespan. Thirdly, explore the possibility of adding a variable frequency drive, commonly referred to as a VFD. Installing a VFD between the power supply and the motor offers a means of precisely controlling both the motor's speed and voltage. This control enables the motor to function effectively even when connected to a 208 volt supply. Nevertheless, it's crucial to acknowledge that VFD can be a relatively expensive solution compared to other alternatives. Fourthly, investigate whether it's feasible to reprogram the existing motor controllers. If the lift station employs electronic motor controllers, there's a chance they can be reprogrammed to enable the motors to operate on the available 208 volts. This solution necessitates technical expertise and may not be applicable to all motor types, requiring a careful assessment of compatibility. Fifthly, consider using a voltage regulator. Installing a voltage regulator ensures a consistent 230 volt supply to the motors. This option may prove to be more cost-effective than opting for a VFD, although it's important to note that it might not offer the same level of efficiency. Now let's delve into some important considerations. It is highly recommended to consult with an experienced electrician to determine the most appropriate solution for specific needs. Factors such as the cost of materials, installation expenses, and potential ongoing maintenance should be carefully taken into account. Give thorough consideration to the potential impact on the motor's overall performance and its expected lifespan. Finally, ensure strict adherence to all applicable electrical codes and safety regulations throughout the implementation process. It's important to remember that operating motors at voltages significantly different from the rated voltage can lead to various issues. Running a 230 volts motor on a 208 volt supply typically results in reduced torque and horsepower output. The motor may also run hotter, which can degrade the insulation and shorten its lifespan. If the voltage drop is severe, the motor may struggle to start under load or stall during operation, potentially causing damage. Now let's talk about transformer specifics. A step-up transformer increases voltage from the primary side to the secondary side. In this case, you would need a transformer with a 208 volts primary and a 230 volts secondary. The transformer's kilovolt amps rating must be sufficient to handle the total load of the motors plus any additional load. When selecting a transformer, consider the inrush current of the motors. Motors draw a significantly higher current during startup than during normal operation. The transformer should be sized to handle this inrush current without experiencing excessive voltage drop. Voltage compensators, also known as voltage boosters, are designed to raise the voltage to the required level. These devices typically use auto transformers or electronic circuits to boost the voltage. While they can provide a relatively inexpensive solution, they may not be suitable for all applications. Voltage compensators can introduce harmonics into the power system, which can negatively affect other equipment. They may also have limited capacity and may not be able to handle the full load of the motors. Now let's talk about VFD. VFD offer a more sophisticated solution to voltage mismatch. They convert the incoming alternating current power to direct current and then invert it back to alternating current at the desired voltage and frequency. This allows the motor to operate at its rated voltage and frequency, regardless of the supply voltage. VFD offer several benefits beyond voltage correction. They can improve motor efficiency, reduce energy consumption, and provide precise speed control. However, VFD are typically more expensive than transformers or voltage compensators. If reprogramming motor controllers is an option, it involves adjusting the settings of the electronic controllers to compensate for the low voltage. This may involve changing voltage and current limits, as well as adjusting the motor's control algorithm. Reprogramming motor controllers requires specialized knowledge and software. It may also void the motor's warranty. Additionally, not all motor controllers are capable of being reprogrammed to operate at different voltages. Voltage regulators are devices that maintain a constant output voltage, regardless of variations in the input voltage or load current. They typically use electronic circuits to regulate the voltage. Voltage regulators can provide a stable voltage supply to the motors, but they may not be as efficient as other solutions. They may also have limited capacity and may not be able to handle the full load of the motors. When choosing a solution, it's important to consider the long-term costs and benefits. While a transformer or voltage compensator may be less expensive upfront, a VFD may offer significant energy savings and improved motor performance over the long run. It's also important to consider the reliability and maintenance requirements of each option. VFDs, for example, may require more frequent maintenance than transformers. In addition to the technical considerations, it's also important to consider the applicable electrical codes and safety regulations. All electrical work must be performed by qualified electricians and must comply with the National Electrical Code, or NEC, and any local codes. The NEC provides specific requirements for the installation and wiring of electrical equipment, including motors, transformers, and VFD. It also includes requirements for grounding, overcurrent protection, and disconnecting means. When installing a transformer, it's important to ensure that it is properly grounded and protected against overcurrent. The transformer should be installed in a well-ventilated location to prevent overheating. The wiring to the transformer should be sized according to the NEC tables, such as Table 310.15b16, based on the ampacity of the conductors. When installing a VFD, it's important to follow the manufacturer's instructions carefully. VFD can generate harmonics, which can interfere with other electronic equipment. It's important to use appropriate filtering to minimize harmonics. The motor should be properly grounded to prevent electrical shock. The wiring to the motor should be sized according to the NEC tables, such as Table 430.22a, based on the motor's full load current. When working with electricity, it's important to always follow safe work practices. Always de-energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Never work alone. Have a qualified electrician inspect the work before energizing the circuit. In summary, several solutions exist for addressing a voltage mismatch between 230 volts motors and a 208 volt supply. These include step-up transformers, voltage compensators, VFDs, reprogramming motor controllers, and voltage regulators. Each option has its own advantages and disadvantages in terms of cost, performance, and reliability. It's important to consult with an experienced electrician to determine the most suitable solution for the specific application, taking into account the long-term costs and benefits, as well as the applicable electrical codes and safety regulations. Consider the following points when making a decision. Evaluate the existing electrical infrastructure and the available space for installing new equipment. Assess the load requirements of the motors and any other equipment that will be connected to the same power supply. Determine the acceptable level of voltage drop and the impact on motor performance. Compare the costs of different solutions, including materials, installation, and maintenance. Consider the energy efficiency of each option and the potential for long-term energy savings. Evaluate the reliability and maintenance requirements of each option. Ensure compliance with all applicable electrical codes and safety regulations. Document all work performed and maintain accurate records for future reference. By carefully considering these factors, it's possible to select the best solution for addressing the voltage mismatch and ensuring the safe and reliable operation of the lift station motors. Remember, safety should always be the top priority when working with electricity. Always follow safe work practices and consult with qualified professionals. Now, let's consider some specific scenarios to further illustrate the decision-making process. Scenario 1: the lift station has limited space for installing new equipment. In this case, a voltage compensator might be the most practical option, as it typically requires less space than a transformer or VFD. However, it's important to ensure that the voltage compensator has sufficient capacity to handle the full load of the motors and that it does not introduce excessive harmonics into the power system. Scenario 2: the lift station is located in an area with frequent voltage fluctuations. In this case, a voltage regulator might be the best option, as it can maintain a stable voltage supply to the motors regardless of variations in the input voltage. However, it's important to ensure that the voltage regulator has sufficient capacity to handle the full load of the motors and that it is properly protected against overcurrent. Scenario 3: the lift station requires precise speed control of the motors. In this case, a VFD would be the best option, as it allows for precise control of both the motor speed and voltage. However, it's important to ensure that the VFD is compatible with the motors and that it is properly programmed to optimize performance. Scenario 4: the lift station has electronic motor controllers that are capable of being reprogrammed. In this case, reprogramming the motor controllers might be the most cost-effective option, as it does not require the purchase of new equipment. However, it's important to ensure that the reprogramming is performed by a qualified technician and that it does not void the motor's warranty. Scenario 5: the lift station has a dedicated transformer that is only used to supply power to the motors. In this case, replacing the existing transformer with a step-up transformer would be the most straightforward option, as it does not require any modifications to the existing wiring or equipment. However, it's important to ensure that the new transformer has the correct voltage ratio and kilovolt amps rating. In each of these scenarios, the best solution will depend on the specific circumstances and the priorities of the facility owner. It's important to carefully evaluate all of the factors involved before making a decision. Remember to consult with an experienced electrician to ensure that the selected solution is safe, reliable, and compliant with all applicable codes and regulations. By taking a systematic approach and considering all of the relevant factors, it's possible to resolve the voltage mismatch issue and ensure the efficient and reliable operation of the lift station motors.